Hello and welcome to our video on Gauss's law. We will be looking at a long uniform line of charge and calculate its electric field. Let's get it started. This is key concepts we'll be looking at. Electric field, strength of long line of charge, electric flux, Gauss's law, and Gaussian surface. Who is Gauss? Gauss is a German mathematician and physicist called Johann Carl Friedrich Gauss. Made a substantial impact on a variety of scientific and mathematical subjects. Gauss is considered to be one of the history most significant mathematician and made a remarkable impact on a variety of scientific and mathematical subjects. One of his notable works is Gauss's law, which was published in 1867. What is Gauss' law? To understand Gauss' law, we need to first look at function of electric flux. Electric flux is defined as rate of flow of an electric field through a given surface. An enclosed surface with no charge always has net flux of zero. Electric field lines are exerted off positive electric charge and are attracted to negative charges. It's also important to know that electric fields are perpendicular to charged surfaces. Now that we know the basics of electric flux, we can understand Gauss' law. The law states that electric flux across any closed surface is proportional to net charge Q enclosed by the surface. This is Gauss' law in integral form, and this one below is a simplified Gauss' law, giving Q in total charge enclosed within V, and electric current is
Gaussian surface. Before we start solving the question at hand, we need to know what a Gaussian surface is. It is a closed three-dimensional space such that the flux of an electric field is calculated. A Gaussian surface is part of the power of Gauss's law in evaluating electric fields of any surfaces. It is also able to evaluate magnetic and gravitational fields. It is convenient to construct an imaginary surface to take advantage of the symmetry of the situation. If the symmetry shows that electric field is constant, then calculating the electric flux can be done by multiplying the value of the field times the area of the Gaussian surface. In this video, we will be using a cylinder surface to calculate the electric field of a long uniform line of charge. Why a cylindrical shape? Well, the reason why we chose a cylindrical Gaussian surface is because it would make our lives easier. As a matter of fact, you can choose any shape to be a Gaussian surface, but in doing so, you will have to use the geometric symmetries of the charge distribution to make the problem simpler. So, the integral form of Gauss's law has a dot product of E and ds. If you want, you can take a cube centered around the line charge, but then you have to integrate over all the angles of E and ds, making them more annoying. You can reduce this effort by choosing a surface where the electric field is always parallel to ds or perpendicular to the surface. That way, you don't have to include any angle consideration as before. Long uniform line of charge. Here we will be explaining what a long uniform line of charge is and deriving a formula to help calculate the strength of its electric field. A long uniform line of charge is known as a distribution along a wide-dimensional curve. Gauss's law will be applied to calculate the electric field of a long line of charge. Gauss's law will be applied to calculate the electric field of a long line of charge. The electric field is directed outward and has the same magnitude at every point on a Gaussian surface that is shaped like a cylinder at radius r. Simply multiplying the electric field by the cylinder's area gives us the electric flux. Consider an infinite line of charge with uniform charge density per unit length, lambda. What is the magnitude of the electric field, a distance r, from the line? First, let's agree that if the charge on the line is positive, the field is directed radially out from the line. If it is negative, the field is directed in. What is the appropriate Gaussian surface to use here? Well, a cylinder of length L and radius r is just what we need, with the axis of the cylinder along the line of charge. To apply Gauss's law, we need to answer two questions. What is the total charge enclosed by the surface? And what is the net electric flux passing through the surface? The total charge enclosed is Q enclosed equals lambda L. the charge per unit length multiplied by the length of the line inside the cylinder. To find the net flux, consider the two ends of the cylinder as well as the side. There is no flux through either end because the electric field is parallel to those surfaces. On the other hand, the electric field through the side is simply E multiplied by the area of the side, because E has the same magnitude as is perpendicular to the side at all points. Net flux equals electric field area equals electric field 2 pi r length. By Gauss's law, the net flux equals Q enclosed divided by epsilon naught. Therefore, electric field 2 pi r L equals lambda length divided by epsilon naught. The factors of L cancel, which is encouraging. The field should not depend on the length we chose for the cylinder. Solving for the magnitude of the field gives electric field equals lambda divided by 2 pi r epsilon naught. Because K equals 1 divided by 4 pi epsilon naught, this can also be written electric field equals 2k lambda divided by r. The electric field is proportional to the linear charge density, which makes sense, as well as being inversely proportional to the distance from the line. Now that we have our formula, we can solve any electric field of a long line of charge. Thank you all for watching the video. Hopefully you are now well informed about Gauss's law, how the formula is derived, and how to apply it to a long uniform line of charge.